Good morning and welcome back. Today we will talk about the last section of our final exam. After this section, we still have to discuss something about synchrotron radiation. Okay. Today we will talk about here, section 14.3. 14.3, radiation emitted by an accelerated or decelerated charge, 加速或减速. But we will focus on angular distribution. Angular distribution. So today we will start with page 34 to 40, just 7 pages, not too much. First, we talk about from linear charge potential. We know the field can be divided into velocity field and acceleration field. And if we use pointing vector is power per unit area at the observation point. 观察者, where is the observation point? Here is the point of observation. Here. Okay, so E field from this one, B field can also relate it to here. That's B field. Okay, so from these two, we can obtain a simple relation. C over 4 pi, absolute value of E squared, and times N. N is from this point to this point. That's the orbit. And at this point, it emits a signal in this direction, N direction. And the signal will reach to here. The signal will travel. So the time will be R over C. During this time, the particle moves from here to here. Okay. This is at time T. The observer is here. The observer sees a signal emitted from here, earlier time. So you can expect equals T minus T prime. Okay. T minus T prime. That's the difference between T and T prime. Earlier time or retarded time. So X radiation in this direction will be here. So we can neglect the velocity field. Why? Why we can do that? Look at this equation. The velocity field is 1 over r squared, and acceleration or deceleration field is 1 over r. So you can imagine this one velocity field will be relatively small compared with acceleration field. Therefore, we can neglect the velocity field and focus on the acceleration field. So here, because of E squared, so we have E squared from here, C over C squared, but we have another C here. So it's 4 pi C E squared. And here is R squared, 1 over R squared. And others are the same. Just write it down. A slightly different. N dot beta. Here is beta dot N, but A dot B equals B dot A, so no difference. In this section, we are interested in the angular distribution of power radiated by the charge. So angular distribution of power radiated by the charge, not received by an observer, okay, by the charge. Give the power per unit area received at the observation point. This is related to the power per unit area received at the observation point here. Just a moment. But actually we care about here. Interest in the angular distribution of power radiated by the charge, received by the observer, radiated by the charge. That's the difference. Power radiated by the charge into a studied angle here is in general different from the power received over an area substantially studied angle. You may imagine the power radiated by the charge will be different from the power received by the observer. The angular distribution. The reason is that motion of the charge toward the observation point will shorten the radiation pulse. If this is the observer, if it radiates a signal and also move in the same direction, then the pulse will become shortened, which results in increased power at the observation point. Squeeze the power, 那个 power 被压缩，被挤压，所以能量被挤压，所以 power 会 increase. On the other hand, 如果这是 observer, a charge move in the opposite direction, so obviously the pulse will be lengthened, will be decreased the power. Okay. At the observation point, because the total energy received must equal to the total energy radiated. Okay, so the conservation is still correct. 能量守恒吧。Total energy received must equal the total energy radiated. 发射的跟收到的能量必须一样。Last, to suppress the power radiated, to express, not suppress, 表示 the power radiated in terms of the power received, we need to determine the ratio dt to dt prime. 这两个的比例必须决定下来。为什么呢？因为 total power 是 energy divided by time， 那 energy 是一样，所以 power 两个 power 之间必定的关系是 dt 跟 dt prime 的关系。Observation time and radiation time, retarded time. OK, 这个我们刚刚已经讲过了。We just talk about this relation. Therefore, dt over dt prime 1 plus 1 over c dr t prime dt prime. Using equation 4, we have these relations. O1 minus n dot beta. Okay, beta is normalized velocity. So this one, the largest value is 2. Smallest value is 1. is somewhere between 2 to 1, 0 to 2. A pulse of duration dt received at x and t is radiated by the charge at r and t prime for a duration of dt prime equals dt divided by 1 minus beta t prime dot n t prime. Okay, note that dt and dt prime are quantities in the same reference frame. In the same reference frame, 同一个 left frame. Okay. Same reference frame, 并不是指 time dilation or space contraction. In the same reference frame. Okay, so here, r squared times this one times dt. A conservation of charge that is in the same reference frame, right? Conservation law must be in the same reference frame. Invariant is in conserved quantity and invariant quantity is different. Conserved quantity should be the same in the same reference frame. Okay. However, invariant quantity should be the same for different Lorentz frames. So we have this one, dp over the omega, dp at time t prime over the omega. So this, but this one, these two are the same. Is with respect to the charge. The omega is with respect to the charge. Okay, up to this point, looks okay, no problem at all. And so we have a simple relations. The simple relations is here. Pointing vector times the radius is the power. Okay, so it's r squared times pointing vector times the ratio between emitter, observer, and the source. Okay, so it's e squared over 4 pi c 1 over r squared. Where is r squared? Or cancel with this one. Go back to, oh, pointing vector is here. Like we have r squared here, so cancel with this one. Therefore, eventually, in terms of power, we have e squared over 4 pi c. And then others are the same, except here. It should be r to the 6th order, but we have extra term here. So you can, sometimes we write this form, sometimes we write this form. Where n beta and beta dot are to be evaluated at the retarded time t prime. Equation 14.138 gives the power radiated into a solid angle in the direction of n in terms of the charge E and instantaneous beta and beta dot. We have beta and beta dot. That's different. Beta is normalized velocity. Beta dot is normalized acceleration. Okay, where is beta dot? Here. Beta here. Okay. Now I will give you 2 examples. I will show you the angular distribution of radiation by a moving point charge. Okay, first, let's consider case 1. B parallel to beta parallel to beta dot. That is, the particle move in this direction and also accelerate in this direction or decelerate. Okay, so just substitute everything into here. Since beta and beta dot in the same direction, so cross term give us 0, and n cross n give us this one. Substitute to this equation, we got this one. So total power, we should perform the 30 angle. We have this one. Let's agree with equation 14.26 and 14.27. Go back to equation 26. That's 27. That's 26. We have different expression. 2e squared over 3c gamma 6. Okay. Oh, 2e squared over 3c beta dot times gamma 6. Okay, exactly the same. Except just substitute beta and beta dot in the same direction. 26. Okay, because this one is 0. In this case, 0. So don't worry, just one terms. So exactly the same. Different derivation, but the same solution. Let's verify our derivation. For beta smaller than 1, which means non-relativistic, Lamar's result with radiation peaking at theta equals 90 degrees perpendicular. Okay, that's normal result. Maximum value, very small, so drop this term. Maximum value is pi over 2, okay, 90 degrees. For beta, very close to 1, the angular distribution is tipped forward more and more and increase in magnitude. Beta very close to 1. Cosine theta will be 0. 0. Because very small, extremely small here and small here. So obviously the power will concentrate at the forward directions with the maximum intensity. The maximum intensity at here. That's relatively easy. You can derive by yourself. Otherwise, it might be appeared in your final exam. Okay, another one is beta minus 1, approach 1. Relativistic extreme. And we have theta very small. Hence, it's equals to this one. Okay. And since beta very close to 1, we can rewrite this one into this one and this one. So 1 minus beta squared over 2, theta squared over 2. So it equals to 2 gamma, 1 plus gamma squared theta squared. Therefore, this one can be rewrite into this one. And sine theta, we can rewrite into here. It doesn't matter. Looks okay. What is the maximum value? Maximum value is actually here, right? This is the maximum value. Roughly about 1 over 2. So the maximum angle value is about gamma times theta is about 1 over 2. the angle of the maximum intensity. 1/2, 1/2, right? And how about the root mean square? Root mean square, 方均根，平均之后开根号，平均平方，然后开根号 ，root mean square. So from this case, it is somewhere about here. Root mean square, roughly about 1/gamma, roughly about very close to 1. Okay, so it's mc squared over E. That's root mean square. Okay, that's for accelerator, for cavity. How about for radiation? Perpendicular case. Perpendicular case. Another condition. Beta perpendicular to beta dot. I'm sorry, this dot is very small, difficult to see. Okay, so in this case, beta and beta dot are perpendicular to each other. And we let beta is in a z direction. Beta dot is in the x direction for our convenience. N is therefore the observation point sine theta times cosine theta in the x direction. Sine theta times sine theta in the y direction, sine phi. This is theta, this is phi. And cosine theta in the z direction. So we just write everything down. So eventually here times this one. The power PT solid angle will be here. Agree with equation 14.31. And on the other hand, you can open your lecture note to 14.31. 14.31. Yes, the same? Right. Good. Pretty good. And go back. And all a different expression, 14.47, different expression, 47. Oh, 47. Just a moment, very close. 47 is not shown here. No, it should be here. Oh, here. Oh, no. I'm sorry. Different expression, right? Different expression. Okay. In this case, it should be 31. It should be beta dot. Let me see. Let me check again. 31. Beta. Oh, perpendicular. Perpendicular. So correct. Okay. We change form. We change form here. We change the v dot square into v square over rho. Okay, so for beta, very close to 1, we have this expression. So theta maxima will be here. Perpendicular acceleration, move in the y direction and change in the x direction. Change in the x direction. And radiation looks like a searchlight, a narrow cone like a searchlight. And the width, the angular width, root mean square angle will be 1 over gamma. So obviously that will be very, very narrow, very, very narrow. Okay, so perpendicular is good for radiation, and parallel is good for acceleration. Different applications. Next time we will talk about, our final exam will cover chapter 10 to 14.3. That is here. That's here. Okay, so next time we will talk about synchrotron radiation. Radiation emitted by a charge in arbitrary, extremely relativistic motion. I will show you next time. Bye-bye and see you next time.